You are currently in the Jasmine room, and this talk is Internet-facing PLCs, a new back orifice. Thank you.
Ladies and gentlemen, welcome to our talk, Internet-facing PLCs, a new back orifice. My name is Johannes Klick, and this is Stefan Lau. We are from the Freie Universität Berlin. And our group is called SCADAX, stands for Scatter and Computer Security. We are consisting of bachelor students, master students, PhD students, and one professor. Our topics are researching in attacks and also doing research in new defense mechanisms for the industrial security. And now I will give you a small overview of our talk today. So at first, we will give you a comprehensive overview of traditional attack vectors in the past for PLCs. Then we will show you a distribution of Internet-facing PLCs in Europe and USA. Then we will explain shortly our attack, which we are showing today. And then we will give you introduction to Siemens PLCs, how they work, for understanding them. And then we will explain, with this knowledge, we can explain our attack in detail, how to inject code into program logic controllers, and how to exactly inject an SNMP scanner or a SOX proxy in a PLC. And in the end, we are doing an evaluation of our attack. So let's start with the traditional attack vector of PLCs. So, well, we know in the past there's a well-known Stuxnet. It has compromised Iranian nuclear facilities through the supply chain. There was a Siemens worker, he attached to an engineering workstation an USB stick, and this compromised the development environment of Siemens for programming PLCs. So this means that if you have programmed a program A, which you want to download to a PLC, then the Stuxnet has modified this code and has uploaded code B to the PLC. So the engineer was not able to see that and thought, okay, everything is running fine. So this is an offline attack. We also know that last year in December, German Steelwork got hacked. So they attacked the business IT via phishing emails, malicious phishing emails, and the attackers were able to get the business IT, and then they worked from the business IT to the production network, and there they have manipulated the industrial control system, which damaged the furnace. So this is just an example picture of a steelwork, and the damaged furnace finished in a certain state. And so it just got cooled, and if you have a huge furnace which got cooled, you can throw it away, right? You have to completely refurbish it, and the damage is expected about to several millions of dollars. And so here you can see a control room of a steelwork, and on the left side from the guy, you can see a SCADA system which controls the steel process. Okay, so we have now an offline attack and an online attack over the business IT. And the question is, okay, what if when one system of the production network is maybe online, like a PLC? So we know we searched on SHODAN for a lot of industrial control systems, and here we have a map. So we see red dots are PLCs, green dots are PLC network devices, which make PLCs internet capable or Ethernet capable. It's like converting. They are converting for bus systems to Ethernet systems, and so we see there are a lot of control systems in Europe, and we also see that we have a lot of control systems in the USA. Here, yellow dots are more building management systems. So because we are Germans, we know which control systems are used in Germany, and we may not knew so good the control systems in USA, but we have found a lot of building management systems. But even building management systems are very dangerous when you hack them. Think on a pharmacy. If you increase the humidity of a process, of the environment, you can maybe throw away a lot of pills. So building management systems are also very important. So we see that in the end, we see that in Europe and USA, you have a lot of control systems online. And here we have some numbers. We did this research in 2013, and we see that the number of PLCs, programmable logic controllers, also SCADA systems, are increasing since 2013. So we have today, in 2015, we have over 30,000 PLCs based on SHODAN data, which are directly connected to the internet. Why are these systems connecting to the internet? Well, mostly it's for maintenance. So sometimes you have adjust the program, something gets more hot or more cold, the environment changes, and that's why you need some maintenance. Guys are putting these devices online, are calling their services and say, okay, this is the IP, please connect to the PLC and reprogram it, right? So, okay. So, but the question is, if you have one internet-facing PLC, you find it on the internet, what is behind? Is there maybe a whole production network, or are there a lot of other PLCs? And our attack will show how we can use one internet-facing PLC for attacking other PLCs in the local production network behind this internet-facing PLC. We will give you now a rough overview. So at first, we have here a production network, and we have 3 PLCs, PLC 1, 2, 3. And PLC 1 is connected to the internet, and also an attacker is connected to the internet. Well, so the attacker injects a scanner into PLC 1. We will explain you later in detail how to inject a scanner into a PLC. So with this kind of scanner, especially we have done it with the SNMP, so it's the SNMP scanner. The scanner of the PLC, so there's a scanner running on the PLC 1, and the scanner now scans the local production network, right? So now we can see that the scanner scans PLC 2, PLC 3, and the rest of the production network. Then the scanner stores its data in a database, in a data block, and then the attacker can download the results from the PLC and has now a rough overview of the production network. So, but, well, getting information of a network we thought is not enough. That's why we have implemented in STL a SOX proxy server, which now is able to run on a PLC. So the attacker now injects malware which provides a proxy, and then the attacker can use the proxy, the PLC proxy, as a gateway for accessing all other devices in the local production network. So we show a completely different way, a completely new attack vector. We know that there was an offline attack vector and an online attack vector of the business IT, and we show how to leverage one internet-facing PLC for compromising the whole production network behind. Okay, and now Stefan will give you some basic information about Siemens PLCs.
Thank you. In order to perform this attack Hannes described, we need, of course, to know some details on Siemens PLCs. In special S7-300 PLCs, I will cover into this introduction, but these concepts can be applied to some of these concepts can be applied to other PLCs as well. So at first, I will tell you what a PLC is, if you don't already know that. Then I will show how the program is executed on the PLC and how does it differ to a normal program on a computer. Then I'm going to show you how a program is structured and how a program on a PLC looks like. So what is a PLC? It is a programmable logic controller, and it is used to control industrial processes, and it is a real-time industrial computer. The PLC has in and outputs. These inputs are connected to sensors which can get the state of the industrial process and its machines. And the program controls then with the inputs, the outputs, and controls the machinery in the industrial process. So how the program is executed? In contrast to the computer, the PLC program is cyclically executed. At the beginning of the cycle, there is a snapshot taken of the in and outputs of the PLC and is mapped to a memory. A snapshot is taken because the user program, which is then executed, needs to have a consistent state of the in and outputs. After that, the operating system takes place and executes some background functions like network communication. So the overall execution time of the cycle is monitored. So if the cycle takes too long, which means the user program does hang or is freeze or something like that, then the cycle is killed and an error is raised in the PLC. So programs on a PLC, on a Siemens PLC, consists of several blocks. A program has at least an organization block, which is the program entry point and is comparable to the main function in C. To store any data, the program can use data blocks to persist it. Additionally, we have, of course, functions which can have arguments and return values. And there are also special functions which can keep a state, which they keep a state in the data block, in an associated data block. To perform special tasks, PLCs have a system library where we can do, for example, network communication. And last, there are some special data blocks called system data blocks, and they are simply used for PLC's configuration and are not used in the program itself. So let's see how a program looks like. We have here a simple Boolean term. We set the first output of the PLC depending on the first three inputs of the PLC, which means output Q00 is true if the first two inputs are true or the third input is true. This term looks in statement list like you see there on the slide. Statement list is an assembler-like language and is an assembler-like language and is the basis of all PLC programs in the Siemens world. So when we compile this block and upload it to the PLC, it is of course stored in binary. Here we see how the binary might look like. Don't let you overwhelm. We just need to know that each binary block has a header. These are the first, a lot of rows there. Yeah. And then there follows the data, which is MC7 bytecode, so the STL representation, or simply the date of a data block. And then we have a footer, which just not only contains the signature, but some other values, which are not necessary for our attack. So let's say we have an OB1 with the STL instructions we saw in the previous slides. And this is compiled to this binary block we see here in the hex dump. So let's take a look at the interesting values we can find here. The sixth byte of this binary is the block type. In this case, it's an OB. Then we have 2 bytes of block number in big endian. Then there follows the total block length of 116 bytes. Then we have some other data which is not interesting, but then right before the code section, we have the code length of 10 bytes. Then we have the MC7 opcodes of each instruction. And at the end, an implicit block end return is added. So how to get these binary blocks onto a PLC? Siemens has a proprietary protocol S7-COM, which is used to manage the PLC and also to upload program blocks. S7-COM is an RPC protocol. Its telegrams are wrapped into the ISO over TCP protocol. The ISO over TCP protocol is used to address several components in a composite PLC environment. So mostly you don't have one PLC like we have there. You have a lot of PLCs. You can have a lot of PLCs with a lot of in and output modules. You can address them with ISO over TCP. And then the whole packets are wrapped into TCP IP. So when we upload a program block, it looks like this. The engineer workstation negotiates a message size called packet data protocol data unit. with the PLC. Then the engineer workstation says, I want to download something, or you should download something. Then the PLC starts the download job, and the EVS sends the block data. Then the PLC acknowledges the download end, and then the engineer workstation inserts the block into the file system, which activates the program block on the PLC. So if you are interested in S7com, the open source community has done a great job. To reverse engineer this protocol, there is an Wireshark dissector, which is pretty good. Also, you have implementation of the S7com protocol available called Snap 7. Yeah.
Okay, yeah. So now you got some basic information about the Siemens PLCs, and now we can explain you our attack details. So, as I told you before, we will now show you how to instrument a live PLC programs with scanning malware, then how we have implemented the SNMP scanners, so we are doing SNMP scanning, collecting the scan results, and then we are instrumenting the PLC again as a proxy, and then we are using the one internet-facing PLC for attacking the devices behind. So again, here we have PLC1, which is connected to the internet. And now the attacker does the following. He downloads OB1, the main function of the PLC. So here you have, as an example, OB1, which looks like that. And what we are doing now is, we know the binary representation in MC7, which is the result after compilation. And now we are adding a call to a function which is under our control and will be uploaded again later. So it is important to notice that Stuxnet did the same. So if you want, Stuxnet has also prepended its own code to the original control code. We are doing the same. And here you can see that we are adding a call, and then the function will be executed with our attack code. It returns, and then the normal control code gets also executed. So this is very important. This means that the normal control of the process get not disturbed. So when we are doing our attack, we will show it later in the demonstration, the control code get not disturbed, the service stays on and goes further. So this makes the attack harder to detect. Okay, now let's look how it looks at binary in detail. So here you can see the purple one is the code. So you have above or on top, you see the code written in STL. And here you can see the code in its binary representation. So you can here see the opcodes, right? It's 8 bytes code. No, it's more. Sorry, it's 10 bytes. So what we are doing then is we want to insert our call to our malicious function we are adding later. So this means we have to add further 8 bytes. So we just need adding 8 bytes for a call that get executed first, and then the normal control code get executed. So now we are adding our call, just only the bytes. In the second step, we have to increase the local block length. Here you can see we have to add 8 further bytes. And then we have to increase or update the code length field. So we are just adding 8 bytes, a new call to a function which is under control, and updating 2 length fields. This enables us to inject an SNMP scanner or a proxy or some other kind of malware to a PLC. So we are releasing here on Black Hat a new tool called PLC Inject, and this tool enables you to, so this tool is doing the following. It downloads automatically OB1, patches it, and uploads OB1 again to the PLC. You have just to provide your own malware, and then it will do the magic for you. Okay, so you can find PLC Inject on GitHub right now. And you have just to, here you can see the main page. You have just to provide the IP address. Then -P stands for block you want to patch. You can also patch another block. It's not, you can also patch a function block or just another organization block, but this makes more sense to take the OB1 because then your malware gets executed first. And then you have to say, okay, which number has your own malicious malware. So in this kind, we say, okay, FB1000 is our function block which contains the malware, and you have just provide the path to this malware. Okay, we will now show it. So, yeah. So here on the left, you can see. So this is a PLC here, right? It's a Siemens PLC. It's the S7-300. It's the same PLC which got attacked by Stuxnet. So here you see a signal column, right? And the PLC is controlling the signal column. You see switching from red, green to yellow and backward. So this stands for the normal control code. Yes, this could be a whole production process, like kicking bottles or, don't know, just making some metal or something else. So this represents a process which gets controlled by the PLC. Okay. What we now show you is PLC inject. We have here column PLC inject. The IP address of the PLC is 10.0.0.1, like in our example. Then we say, okay, we want to patch OB1. And this is our function which should be called. And this is the path where our function is inside. Okay. So then we say, okay, that's only for demonstration purpose only, and so on and so on. We say, yes, please patch it. And now the PLC got patched. And you see, now we are executing here a second. So we are now executing additional code, right? But the normal code got not disturbed. So this is a normal controls process, right? So it's blinking like before, and now we are executing additional code. So this could be an SNMP scanner, a proxy, or every else malware you're thinking about you want to design. So this tool enables you to fully inject malware into a PLC without service disruption. Okay, now we have shown you and explained to you how to inject your own programs into your internet-facing PLC. So here we can see in our attack we have done in our laboratory, we are uploading, so we have downloaded OB1 before, we have patched it, we have modified it, and are now uploading the modified OB1 again, and our malicious function which gets called by OB1. Then the PLC1 runs our SNMP scanner, additionally to the normal control code, and scans the local production network. Then the attacker downloads the data block, has the overview of the production network. You need to know that, that's very funny, Siemens systems have SNMP enabled by default, right? So this means I will detect every fucking Siemens PLC in the local production network. So, and this is not enough. The PLC is talking a lot via SNMP. It tells you the serial number, it tells you the firmware revision and the hardware revision. So I can easily look up for fucking exploits on the internet. Okay. So now we have downloaded the data block, and now we are injecting our SOX proxy, which enables the attacker to use the PLC1 as a gateway via the SOX proxy protocol, and for accessing all other devices, and for accessing all other devices. So we will show you later in our demo video a CVE that we have disclosed to Siemens in March, and where it's a DNF service exploit, and we tested it in our laboratory. So we use PLC1 as a SOX proxy and have tunneled our exploit through PLC1 and have driven a denial of service attack on PLC2 using the TSOX library for tunneling our exploit traffic through PLC1. So now a good question is how to implement an SNMP scanner on a PLC. You know, normally a PLC is constructed for doing control tasks and not for scanning the network or for doing proxying. So this will be maybe some difficult to understand for you, but we are presenting it for people who are very close to the topic for PLCs. So at first, we need to say that ping is not possible with Siemens PLCs because we have only access to the transportation layer according to the ISO OZ model. So TCP is not adequate. The problem is we have only the chance, so we have only the possibility to have 8 concurrent connections. And if a PLC, Siemens PLC, tries to connect to an IP port combination which is not available, it keeps in a busy mode, right? So at first I try to connect IP1 and it's not there. Then I have just still seven further connections. I try to connect IP2 and it's not there, okay, then it keeps also busy. So this means I can only scan up to 8 missing IPs and then it's busy and you cannot close the connection. So it's very stupid design from Siemens, but it protects Siemens from using a TCP scanner, you know? So, well, but that's why we have chosen UDP. UDP is connectionless and does not need a connect setup, so we have unlimited connections, right? Okay, yes, and as I told you before, SNMP is enabled on many Siemens PLCs, and a lot of network devices have enabled SNMP too, right? Okay, so here we see okay, so at first you have to think about one thing. We are injecting an SNMP scanner into a network. We are not knowing how it looks like, right? So at first we need to get the IP address and then the subnet. And then we can say, okay, this is your IP address, this is the subnet, please scan from 111 to 222, right? Okay, for this, the PLC has a kind of global configuration database. It calls system state list. And we are calling the read system statement list function called rdsyst. And this ID there, 37 with the index 00, will give you the information about the local IP address and the used subnet. And this gets stored here in the database IP info. So sometimes if the function sometimes this function is some busy for some milliseconds, then we are waiting until the function is ready, and then we are going further, setting our state, got IP, that we got the IP, and going to the next state. So programming PLCs is quite different. It's like building up a huge state machine and thinking which state I am and entering every time the new state. So now we have our IP address. So we are loading the IP address on the kind of PLC stack and doing a bitwise AND operation with a subnet mask. This gives us the first IP address of the local subnet range. And then we are storing this value here. In the next step, we are loading the subnet mask and doing a bitwise XOR operation here with the subnet mask. It's like inverting the subnet mask, which gives us the number of hosts inside the subnet. So now we know the local IP address, we know the subnet mask, we know the beginning of the subnet, and we know how much hosts are inside the subnet. So we have now every information for scanning the production network. So getting a connection. So this is you have to call tcon. Tcon is like a socket operation in C. And on PLCs, you're not talking about socket, you're talking about so-called connection IDs. So here we have connection ID 1. And this gives us connection ID 1. And it's quite crucial. You have to call this function 2 times because this function needs a rising edge. This means here you have the REQ value, and if you're calling it first, the REQ value here has to be false, and calling it a second time, the REQ value has to be true. And if the function detects the rising edge, then it will firstly execute it. We are doing toggling the value from false to true here in this area. So this providing us a connection ID 1. So, and then we can call the function TUSend, which enables us to send the UDP packets. And here we can see that we just need to provide the SNMP get data field where the SNMP packet is inside, which we want to send. And we just need to provide a further address, which we want to connect to. So, and then now we can get the IP address information, we can create a socket, and then we can send over the socket UDP packets, in this example, SNMP get request. Okay, now Stefan will explain you how the SOX proxy is implemented in STL on a Siemens PLC.
Right. After implementing an SNMP scanner, SOX proxy seems to be pretty easy. SOX is a pretty simple protocol. You have simple messages. After that messages, you start to tunnel the connection. That seems pretty easy. Why we chose SOX proxy? SOX proxy is supported by all applications. And it's easy to have, if you have an application, it's pretty easy to add SOX proxy support later, as I will show you later in the attack video. So we implemented the SOX5 protocol, and we have a minimal feature set to keep it simple. We support no authentication and no encryption at all. And also we only support a connect request with a TCP stream. So, as Hannes previously said, most applications on PLCs are modeled as state machines. Here we use a jump list to implement the state machine of a SOX proxy protocol. In line 3, you see the first state where we simply use the tcon function, which Hannes shown before, to set up a connection, but we use it in passive mode, which means we simply listen on the SOX port. Once the client connects, we go to the negotiate state. The client sent us a packet which with authentication methods he supports, but we just ignore it because I said we support no authentication, so we sent him an authentication offer of 0, which means no authentication at all. Then the client has to send a connect request, which we receive here. The connect request contains the IP and the port of the destination host he wants to connect to. Once we receive that packet, we simply take that IP and prepare the data structure for the tcon function and copy the IP and the port into it. And then we go to the next state where we start connecting to the destination host. Here we see again the usage of the tcon function. As all asynchronous function calls you use in the system library, we also have to trigger rising edge on the rec parameter in line 4. So in line 12 and 13, we simply toggle connect from false to true, jump to the beginning of the state again, and call tcon again with connect parameter of true, and now we have our rising edge. Then we can wait several cycles until the flags indicate that the connection has been established, and then we jump to the next state. Once we reach the next state, we have two connections, one from the client to the proxy, one from the proxy to the destination host, and we can simply start sending every data we receive from the client to the destination host and vice versa. And so we do proxying. Once one partner closes the connection, the tReceive function mentioned earlier indicates an error. Then we have simply to send the remaining data to the other partner who did not disconnect. And then we can reset the proxy and wait for the next client. So we measured the performance of the SOX proxy implementation. Alone, the SOX proxy on its own is able to transfer up to 730 kilobits per second with a 100 megabit connection. Kilobyte. Not pretty good, but it's okay. Kilobyte per second. So when we have another program on the PLC which is pretty intensive and has a cycle time of around 85 milliseconds, then we were just able to transfer up to 40 kilobytes per second. Now I'm going to show you the whole attack cycle we described in a video. Here it is. So we have the same setup as we've seen before. We have PLC1 with IP 10001, which is connected to the internet and reachable by the attacker we see here. And the other PLCs are not available. To find this PLC, the attacker here uses the tool PLC scan, which was released by the SCADA Strangelove team. So we scan here the whole subnet of 10000, and we find one PLC. So after finding the PLC, we use our PLC inject tool to list all blocks. This is also supported. So we can check whether the block number we want to, our malware has, if it's already taken on the PLC and we don't want to override existing function blocks. So here we have just an OB1 and a lot of configuration data blocks. So after that, the attacker can inject its SNMP scanner. Right, we patch OB1, insert a call to FC1, and provide a path to our malware. So during this whole attack, we had an T-Shark instance running in the background, which we will see right now. The T-Shark simply captures all traffic, all network packets on the network. And there we will see, after we injected the SNMP scanner, we'll see on the last 4 lines, we see that PLC1 immediately starts sending SNMP GET requests, and PLC2 and PLC3 responds to this request. So now the attacker can download the scan results. He uses a PLC dump tool, which is not publicly available, but you can create this tool on your own with step 7. It's pretty easy. So we use OD to display the relevant part with the IPs. We see that PLC 2 and 3 were found. Now the attacker knows on which IPs the PLCs are running on. Now we can inject its SOX proxy and connect to these PLCs. Once again, we patch the PLC. Now he can check what blocks are on PLC2. To do so, we use TSOX. TSOX is a so-called proxyfier. It enables any application to use a pre-configured SOX proxy. Right now we see there are a lot of blocks on it. So we can also download the blocks with the PLC dump tool we used earlier to download the scan results. So we developed also a disassembler for the MC7 language in our SCADAX group. Now we can see which instructions are included into OB1. Now we can also stop PLC number 2. For this, we are using the Metasploit module presented by
Dylan Beresford
at Black Hat 2011.
Yes.
So we are firing Metasploit up with TSOX again to reach proxy PLC number 2. We are loading the module, configuring it, starting the exploit. Yeah, it stopped. Now we see it's running, and now stop.
So this attack was done over one PLC and attacked the other, right? So using TSOX enables you to tunnel your attack over a SOX proxy server, and we have done it here.
Right, and the same way again, we can do this with our exploit we discovered in March. We are tunneling the exploit traffic through the PLC1 onto PLC2. Here we see a lot of ISO over TCP packets, which are transferred via the SOX proxy protocol to the PLC number 2. We're sending a lot of packets, and then the PLC dies. And we can't transfer some packets anymore to this PLC. It won't simply answer.
So having this exploit and the possibility to use the SOX proxy server, this means we could completely run a huge denial of service attack on a whole production network and disabling a factory, right?
Right. Now let's get to the evaluation of our attack. Because the problem is when we add additional code to an almost existing code, we increase the execution time. And the problem is, if we increase the execution time too much, then we are going to hit the configured maximum cycle time, and the PLC will simply stop or raise an error condition, something like that. Per default, Siemens PLCs have a maximum cycle time of 150 milliseconds. If the cycle time exceeds this value, then it is usually stopped or starts another error handling program. But how to measure the cycle time? Cycle time measuring is pretty simple. OB1 has a special variable where he stores the previous cycle time. We simply take that value, store it in a data block. Then we can download the data block from this PLC and have a series of test values which we can analyze. We tested 3 different scenarios. We used the baseline program, which does a lot of memory-intensive info operations. And then we have 2 scenarios where we uploaded the proxy. In one, he was idle, and in the other one, we downloaded a huge program through this Fox proxy. So as we can see, we have a box plot here with the measured cycle times. The baseline and the proxy idle seems pretty equal, but we did a statistical significance analysis whether these test series differ. And yes, indeed, they differed. You see it with the bar above and the 3 stars. And when we put the proxy under load, the cycle time increased a lot. And of course, there was a statistical difference too. So here we see the values we measured. You can see that the proxy under load adds around 1.3 milliseconds to the average cycle time. But if we take the maximum default cycle time of 150 milliseconds, that fraction is only 1%. And in this case, it's not very likely that we will hit this maximum cycle time and render the PLC, put the PLC into an error mode. Yeah, and if you have internet-facing PLCs, how can you protect yourself against these kinds of attack? Pretty easy, stay secure, use VPNs, use firewalls, don't connect them directly to the internet, protect them. There's another way to protect them. Siemens PLCs have a feature to do a read and write protection on this PLC. But it's only, you can't upload and download the program, but you can still manipulate the memory of the PLC. You can still run this Metasploit module and stop the PLC, and that's not a pretty good protection. Otherwise, you can stay connected to the internet and hope nothing bad happens. Yeah, what have you seen? We were able to inject malware to a PLC and do not disturb its operation. Also, we can use an internet-facing PLC as a gateway onto the local network. And an attacker can, of course, then compromise the devices behind this PLC. And when we take this into account, the attack surface on the internet of internet-facing PLCs can be pretty bigger than we already saw with our SHODAN data.
Okay, thank you, ladies, for your attention. Now time for Q&A. You have some questions? Yes, here in front.
Is the maximum program cycle time, is it programmable?
Yes.
Yes, you can configure the cycle time.
The question was, is the maximum cycle time of 150 milliseconds programmable? Yes, it is. You could program the time, and we could also increase this time, including our malware stuff. It's possible, yes. Yes. Yeah, that's true. You can do it, right. Yes.
I guess with the data you can disrupt the process, the production process that allows you to control by the PLCs. But my question is, how do you make sense or somehow identify a logic behind what the PLC is actually doing, so you are able to control the process.
Hast du die Frage richtig verstanden jetzt gerade? So let me ask. So you're asking how can we know what the PLC is doing, right?
Yes.
So, well, that's really hard. We have the disassembler, which makes it possible to see the STL code. We know there's also in academia some projects which are trying to do it with symbolic execution to look which states are possible. And they were able to say, okay, this is maybe a traffic light control. But, well, it's really hard. But this is not the topic of our talk. We just want to show how to use a PLC for attacking the devices behind. So if you just want to run a deny of service exploit, if you're a really bad guy, so you don't care. But in fact, it would be cool to know this. And imagine we Germans are building cool cars, right? So, but if you are hacking BMW and you would decrease the millimeter of the thickness of the car, it could, well, you could throw away a lot of German cars. And so kind of slightly attack would be really, really hard. And for this would be really cool to know what the process does. You're right. Okay, question over there.
Did you ever brick any of these devices, and is it possible to, or how hard would it be to brick the PLCs?
Break? What?
Brick them.
Okay, yes. So we have not bricked one. We are just able to, we have just found the deny of service exploit. And if you run the deny of service exploit, you have just to go there and switch the PLC off and switch the PLC on. But you have to do it manually, and you have to be in front of the PLC. So, but we have not bricked it already, so no. Yes?
Are any interruptions to the program that you're running when you're using blocks? So does that depend on like the size of the program you're switching?
Was hat er gefragt? Ich habe den Kurs nicht verstanden. Can you maybe speak louder? It's hard to understand you, sorry.
When you push your new program, is there any interruption to the program that's already running on the PLC? Does that depend on how many your program was?
Yes, that's a very good question. No, there's no interruption. So we have shown it in the demo, right? So there was this signal column was lightning, was controlled by the PLC, and we have patched the OB1, and then the second one got active, but this was still working fine. The PLC does it like the following. So you have the OB1, and then you get the new OB1, and then this PLC on the next cycle, which gets executed, just switched over, okay? And so the PLC get not disturbed by patching it. And that's very important. That's a very good feature of a PLC, because if you want to doing a live patch for if you're an electrical engineer, you have to do some reprogramming. It would be really uncool if your system would stop because it would disturb the control process. So that's a really good feature of Siemens PLCs, that they have the switch over possibility for changing old code to new code.
And even if you send a large block to the PLC, as we see here in the sequence diagram, it does not overwrite actually the original block. Just when you call this insert function, then the actual block is overwritten. So it's a pretty fast operation, and you do not probably do not disturb the PLC.
Okay, next question, over there.
Plan on extending your research to other PLC vendors?
Yeah, it's a point of time and money. But yes, it would be very cool. And we have now a German research project where we are scanning on Germany for industrial control systems. And there we will get some new PLCs also from other vendors like Rockwell or ABB or Phoenix. And then we will try to apply this attack. Yes, we will do some research, hopefully. Okay, yes. What?
Logs. Logging.
Or if the PLC does some logging. Well, I don't know. So I think no. I have not seen any kind of logs. You have seen some kind of logs?
No, on the PLC there are no logs. But maybe if you have some kind of firewall which simply opens the port and captures the traffic and logs it, then it would be possible. But the PLC itself doesn't log these program modifications.
Yeah. And these systems are really old, right? So if you have a Siemens PLC, you're putting it in a production. The life cycle of a PLC of this type is about 25 years. So we are talking about devices which are set up in the 90s. And that's why we have the problem of the 90s, right? So, okay. Further questions? Yes?
Is PLC inject exploiting a vulnerability, or is that accepting an
PLC does not exploiting vulnerability. Well, this device is vulnerable at all because just protection is a proprietary protocol. If you know the protocol, you can download and upload code. You're using the normal function provided by the PLC. We are now able to understand the protocol, and that's why we can do this. It's like in the 90s where we have no authentication or no encryption, and it's the same here. So it's no vulnerability, it's a feature. Yeah.
You mentioned that you have disclosed some of your research results to the vendor.
Well, we have just disclosed the denial of service exploit we have found, and we have not disclosed this because to every electrical engineer we have talked to and we have shown him this kind of attack, they said, well, what the fuck, you're right. I'm doing programs these PLCs all the time, and now if I would think like you, I could do this also. So this should be also known to Siemens that you can do it. We are not doing something hidden or so. It's just a new idea how to compromise the systems. So we have not contacted Siemens. Well, they are now contacted now here in Black Hat. Why is this talk? Yeah. Well, we know that for the 1200 and for the 1500, there's a new protocol. And we have not investigated this protocol very much. And even this open source community is trying to reverse it. And there are some, we know some knowledge about it. We have also found a flaw in the protocol last year, which also was a denial of service exploit. So as I know, there is some kind of authentication scheme now in the new protocol for the 1200 and the 1500. But also there we have to do some further research. Okay, so last question. Time is over. Okay, great. Thank you very much.
Yeah, thank you.
Great audience.